Hi, and welcome to Allen High School's discussion of bonding at the pre-AP or 10th grade honors level. We're going to be moving now into Lewis dot structures of covalent molecules. You've already done it for ionic. You watched Ms. Marusik's videos and found out just how incredibly wonderful she is. And now we're going to do it for covalent molecules. Now we have a list of guidelines here, and I'm going to walk through them quickly, but this is one of those things that's best done, best shown than just read through. So I want you to take a look. I just want to fill in your blanks. This is the least electronegative. Typically the least electronegative goes in the middle, with the exception of hydrogen. Hydrogen can never ever be a central atom, nor can fluorine, which is logical because it's never ever the least electronegative. It's always the most. Now we're going to use 2 electrons per bond. So we'll use dots again, and 2 electrons will be a bond. It's common to write a dash for those 2 electrons. I won't do it very often, but it is quite common to do so. So it's up to you. Start satisfying around the atoms to satisfy the octet rule. All right, most elements want 8 electrons to be stable. What that does is it maximizes attractions and it tends to minimize repulsions. So there's a reason for it, repulsions. You get the idea. I can't spell repulsions, but hopefully you heard it. Okay, repulsions, okay, is that stable 8. But there are some exceptions. I mean, we can make rules, quote unquote, but atoms don't behave like we tell them to, kind of like cats, because my kitties over here drive me crazy too. All right, now I like to think of a Lewis dot structure of covalence much like a potluck. So everybody brings to the potluck what he or she can afford, and then our goal is that everybody leaves satisfied. But we don't all have the same appetites, and hydrogen's one of those that comes in with just a very, very small appetite. Hydrogen's happy with 2 electrons or 1 bond. It's just too small to ever have more than 2 electrons or 1 bond. So don't ever put more than 2 electrons or 1 bond on your hydrogen. Beryllium, and then you're going to say, oh, but Dr. Leggett, beryllium is a metal. Well, it is, but it's so small that sometimes it's reticent to give up its electrons, so it kind of plays the covalent game. And it's happy, I'll just put X's here to represent another element, with either 4 electrons or 2 bonds. Okay? And then finally, boron, and by the way, you have to memorize these top 3. Memorize. And I'll show you a trick that might help you in just a minute. Boron has 6 electrons around it, or you'd see boron with 3 bonds. All right. Now, hydrogen is in group 1 and it has 1 bond. Okay. Beryllium is in group 2 and it has 2 bonds. And boron is in group 13 and it has 3 bonds. And then after that, it's going to follow the rules in terms of being under 8. Now, if an element is in greater than or equal to the 3rd period, it's large enough to accommodate more electrons, and you'll have more than 8. But here's the deal. You don't have to memorize them because the formula will force you to do it. And I think you'll see that as we get moving here. Now, I like to think of the central atom as kind of the mama. And so I always start filling up mama first. Others do peripherals, and that's just fine. If you go to tutorials, it all works out the same in the end. But I satisfy mama first, and then if I'm deficient, I look to mama to give some more help. And if I have extras, I give them to mama, because I know mama will take good care of them. All right? So I satisfy my central. And I think this is for deficient. If we have peripheral atoms that are deficient or do not have 8, they need more. Deficient means not enough. We'll double bond. Okay? Now, we're going to do this really, really random structure concept here. So I'm going to do water real quick. Water looks like this. Now, I know it seems random, but it will help you memorize in the end. We use ABX. Some books use AXE or there's a variety of letters. It doesn't matter. The key is using this to memorize. So if you can get to your Lewis dot and figure this out, the A represents the central atom. And we can define a center if it's a large molecule. We just define one atom as a center while we zero in on it, what it looks like around that atom. We use B to represent peripheral atoms or peripheral groups of atoms. In this case, I have 2 hydrogens, so I'm going to put AB2. And then finally, we use X to represent the non-bonded pairs. So X is going to be, and it's non-bonded pairs on the central atom, not on the peripherals, just on the central. So non-bonded, it's pairs, they're not bonded to anything, and it's only on that central atom. Now I know it seems random, but pretty soon it's really going to help our memorization a lot. If you can get from the Lewis to this, then we'll memorize what structure this is. All right, let's do a few. Let me show you how I got that water one. The first step is to count up valence electrons. That's like saying, what did everybody bring to the potluck? Well, I have 2 hydrogens. They're in group 1. They each bring 1 electron. I have 1 oxygen. It's in group 16, so it brings 6. There are 2 s electrons and 4 p electrons for oxygen. So that gives me a total of 8 electrons. So here's what we want to do. You put the least electronegative in the center unless it's hydrogen or fluorine. In this case, it's got to be the oxygen. Now, I'm not trying to get to any 3-dimensional structure here. So just lay it out in a square, or if there's more than 4, just start circling mama. All right. Now, then what we want to do is start building up the Lewis dot. So for me, I like to make my bonds. So it takes 2 electrons to make a bond. I've used 4 of those 8. I have 4 left. Then I like to satisfy my peripheral. Notice that we're adding these in pairs. All right. Now, if we take a look at oxygen, oxygen now has 8 electrons around it. But look, hydrogen has 2, and it's satisfied with 2. And this hydrogen has 2. It's satisfied with 2. They share, so the electrons count for both atoms as we're trying to determine whether it has that stable octet. Now, we just did this one already. This was an AB2X2, right? Now let's do HI. Hydrogen comes with 1 electron. I have 1 iodide. It comes with 7. That's 2 S's, and then there's 5 in the P block for a total of 7. There is no center when you have just 2 atoms. You need 3 to define a center. So that's not really applicable here. So I have hydrogen and I have iodide. So step 1, make your bond. Step 2, well, there's no center, so we're going to just start satisfying. Hydrogen, remember, is satisfied with 2. So the hydrogen is okay. So I've used 2, 4, 6, 8. Who do you that has 8 and hydrogen has 2. So you notice, got a stable octet there, and hydrogen's happy with that little duet. All right, let's do beryllium chloride. Beryllium is the least electronegative, so I'm going to put it in the center, put the 2 chlorides on either side. Beryllium is in group 2, so it brings 2 valence electrons. I have 2 chlorines, and they each bring 7, so I have 14, 15, 16 electrons. Now this is where your memorization is going to be key. Make your bonds. Now I like to satisfy my central, but you have to remember that beryllium is small. It will only accommodate 2 electrons. So then I'm going to satisfy my peripherals, and I'm going to do it 2 for you, 2 for me, 2 for you, 2 for me, 2 for you, 2 for me. I've used up all 8, all 16 actually. They both have 8 on either side. I have the central atom, that's the beryllium, and I have 2 peripherals. Now, there are non-bonded pairs, but we're only looking at non-bonded pairs on the central atom. And there are no non-bonded pairs on the central atom, so there is no X. Okay, kiddos, this is long enough for a video. You said you liked them short, and I'm going to shorten this one. We'll do some more Lewis dot in our next video. So until then, this is I hope I'm becoming your beloved chemistry teacher. Take care.